Okay, we're going to do section 11.3, which is partial derivatives. To begin, though, we're going to do a little refresher on back to your definition of a derivative that you learned way early on in calculus. So in calculus, you learned that if we had g of x, so I'm going to do like Calc 1 here. Okay, we learned that if we have a function like g of x, I'm going to use g because I'm going to switch to f when we talk about the Calc 3 stuff. G prime of x then was the limit as h approached 0 of g of x plus h minus g of x over h. Okay, and if you remember, we wrote out all those difference quotients and figured those out early on before you learned your derivative rules, your differentiation rules. Okay, in Calc 3 now, multivariable, so we have a function of both x and y. Okay, so what we do is if there's a function in both x and y, in other words, z equals some function of x plus some function of y, and you're supposed to take the derivative, now you have two independent variables, x and y. So we can't do the same thing we did in Calc 1 because it's like, what do you take the derivative of? Okay, with respect to, I should say. Okay, which one do you choose? So we take what's called partial derivatives, and we're going to go over all of the different notations for it, but the one that you're going to see most often would be something like this. It's an f with a little subscript x. Okay, that means you're partial with respect to x of that function. Okay, and that's your limit as h goes to 0 of f of x plus h and y minus f of xy over h. Okay, basically you treat the y as if it's a constant. So this is your partial derivative in x or with respect to x. You might see both of them. Let me see if your book has a specific one they choose. They don't really. Okay, partial derivative with respect to x. So you treat y as a constant. Oops, a constant. Okay, and then we can do the same thing with y, and we will be doing the same thing with y. Your partial with respect to y then, let me make sure that that's clear that that's a 0 there. It almost looks like a 6, which won't make any sense. Okay. That's going to be your limit as h goes to 0 of f of x y plus h minus f of xy over h. Okay, and that's your partial derivative with respect to y, and we treat x as a constant. Okay, so I said I'm going to talk about some notation here. Your partial derivative with respect to x. Sometimes we just write that, okay? Sometimes instead of your dy dx that you learned in AB, we do this little kind of curly d, f dx, okay? So that you can look in your book too, that kind of curls over. Or we could do the derivative with respect to x of f xy, okay? Or dz dx, okay, because usually it is z is your dependent variable. Z equals some function of x and y. We can also have, sometimes, you won't see this very much, your first partial like that, or d1f or dxf. You really won't see those last two that often, okay? But the first ones you will, and we could do the same thing with y. Your partial with respect to y, which might be shortened to this, These are the ones that you're going to see the most often. Maybe this one. Sometimes this one. Not really the other ones, which would be 2. Okay, so there's all the different ways that you might see it written. We got some examples here. It's actually kind of fun once you get the hang of it, I promise. Okay, so here's an example. If we have f of xy is x cubed plus x squared y cubed minus 2y squared. Okay, we might find our partial with respect to x. Okay, so we're going to treat y's as if they're constants. Okay, so with respect to x, that first term would be 3x squared. Second term, think of y cubed as just a constant. Okay, so our derivative of x squared is 2x. Just like that. Okay. And then if y is a constant, when we take the derivative of 2y squared, it's 0. Okay. We could do the same thing now for your partial with respect to y. Okay, if y is our independent variable, x is a constant, the derivative of x cubed is just 0. The derivative of x squared y cubed would be 3x squared y squared. And then the derivative of 2y squared would be 4y. Okay. And if you can't wrap your brain around that, just replace. Think about this. What happens when I say take the partial with respect to x, just treat y as a constant? Put constants in for y. Make it f of x equals x cubed plus, I'm going to make y be 2, so 8x squared minus 8. What's the derivative of that? It's 3x squared plus 16x plus 0. Okay, and if I plug 2 in for y, I'd get the same thing as that. Okay, so sometimes it's hard for kids to wrap their brains around this constant here, this y cubed. Okay, but it's just the same as if we had like an 8 out front, right? It doesn't go away like it does with the second one. It stays there. Okay. We can evaluate these at specific values then too. So if we wanted the partial of x at 2, 1, then that would just be 3 times 2 squared plus 2 times 2 times 1, right? So we would get 12 plus 4, which is 16. Okay, if we did a partial of y at that same point, okay, let's see here. We'd have 3 times 2 squared times 1 squared minus 4 times 1, which is going to be 12 minus 4, which is 8. Okay, I'm actually going to, the function itself at 2, 1, let's see, that'd be 2 cubed plus 2 squared, 1 cubed, minus 2 times 1 cubed. So you'd have 8 plus 4 minus 2. 8 plus 4 minus 2, yeah. Okay, so that would be 10. Okay, so basically what those 3 pieces of information tell me is that we have a point at 2, 1, 10. So 2, 1, 10, maybe up here. Okay, and if I were to move in the x direction, okay, so parallel to the x-axis, as x gets bigger, which remember that's this direction, z is going up by 16. Like that instantaneous rate of change, right? Remember, it's a curve. But we have like this very steep slope. It's going to be hard to draw in 3D. Parallel to the x-axis. Okay, whatever's going on that curve, it's increasing at that point As x increases, z is also increasing, and so is y. And we'll get another 3D figure in here too. If I move parallel to the y-axis, I'm also kind of moving up, okay? Think of it as like you're standing on a hill, right? And if you look, let me think, if you look straight ahead, it's going up, and if you look to your right, it's also up. Look, I'll get a better one here in a second. I feel like it'll be better when I can get I've got a graph that I'm going to show you too. Okay, but this is, again, this is the rate of the change in the x direction. This is the rate of change in the y direction. If I take one step in the x direction, I'm going to take 16 steps in the z direction. If I take one step in the y direction, I'm going to take 8 steps in the z direction. But just remember, it's instantaneous. I'm kind of simplifying that as like an average rate of change. Okay. Yeah, I'll get a graph up here in a second. Actually, let's do this. So in 2D, when we talk about a curve, oops, I meant to do that in black. This will simplify. This will make it a little clearer. In 2D, okay, if I have some curve, okay, and I take a point on that curve. I'm already getting slow here on this. Okay, and then this is y equals f of x. Okay, your slope there, slope of your tangent line is dy dx. And it tells you if I move, in this case, as I move in the x direction, that slope is telling me that I would move in the y direction at that specific point, positive. Okay. Now in 3D, let me see if I can get a good 3D drawing here. I might have some kind of like a mound shape here. Let me try to draw this a little bit. Something like this, maybe. Some level curves on there. Okay, almost like an igloo shape, kind of. All right, and I've got a point on here, like maybe it's right here. Okay, and that should be on that surface. It's not in the middle there. It's like on the surface, just like the point on the curve here. It's right on the curve. Okay, I'm right on the surface here. So some point x, y, z. Okay, and this whole curved surface is some z as a function of x and y. Okay, then if I look, okay, at this point, maybe it's got a y value of like 2 at that point. Okay, whatever it is. So think about following that along the curve parallel to the y-axis. Okay, I'm sorry, parallel to the x-axis. So that little blue curve there, think about just taking a slice out of this igloo and you're parallel to that x-axis there. Okay, and you can almost see it like it's a parabola there, right? And I could get the slope of the tangent line right there. Okay, I'm going to label this as T1. Okay, so this would be the tangent line with y constant. Okay, now if I kind of think similarly, what's a good color here? If I were to slice through that point at whatever x value it's at, okay, and kind of just take that slice parallel to the y-axis there, okay, then I've got a tangent line that's parallel to the y-axis. We might call that T2, okay, with the tangent line with x constant. Okay, so T1 is parallel to the x-axis. Okay, and the slope of t1 would be this partial derivative of z with respect to x. Okay. Got that flipped upside down, don't I? No, I don't. Yeah, I do. I got it flipped up. My pen. Let me fix that. dz dx. Think about that for a second. Okay, and then if we look at T2, that purple line that I drew in, that's parallel to the y-axis, and the slope of T2 is dz dy. Okay, so you can see, like, if I were a little guy standing at that point there, okay, this is what I was kind of saying when I'm standing on the mountain, okay, right at that point. If I look this direction, I'm going uphill along T2, okay? If I look, let's see, this way it's going down. If I look towards the x-axis, I'd be going downhill, okay? And that can change based on where I am on that mountain, but it's telling me exactly what I would do. So like in this case, dz dx would be less than 0, because as I look towards the positive x-axis, it looks to me like I'd be going down, okay? And in this one, T2, dz dy would be greater than 0. Oh, actually, it would, I'm sorry, it would be less than 0. I'm getting my positive and negative mixed up. Okay, if I were to look towards the positive, towards the positive y-axis, I would be moving down. Okay. All right. So kind of think about that. It tells you, like, well, just 2 directions of movement, right? How am I moving along parallel to the y-axis? How am I moving parallel to the x-axis? Okay. I'm going to do another one, which I have a good drawing of. I think just in case this starts to get glitchy, I'm going to stop it here. I'm going to stop this recording. I'm going to make another video, okay? Because I know that these sometimes slow down if I start to write too much. So I'm going to stop this one here.